Hello, hello. I'm back again. We're going to take a look at related rates, which is something you see in first semester calculus. And related rates have to do with if you can think of y and x as two variables, but they themselves depend on another variable, for example, time, so that it's like what we call a parametric equation, where we have x and y, but we have this third variable that's in the background that we can use that to parameterize. So let's start with the problem here that I wanted to show you about. And so if I take a look at this problem here, so we have this distance x, as you can see I have here. That's a wall, and then I have a ladder, and then this distance is y. You can see that's right there. And then the ladder that's on from wall is going to be 20 feet. So that's my hypotenuse of a right triangle, right? And then they tell us the rate of change at which this bottom part of this thing is moving. What speed is this thing moving away from the wall? Well, it's moving away from the wall right there, you see, at 2 feet per second. So the question is, can we find a related rate such that we can tell the way that this thing will be, what rate it will be moving down the wall as that one moves away from the wall? See? So what we want to find is see if we can find dy dt. So that's the way y is changing with time when y is 12 feet. Okay. So if we take a look at this Pythagorean theorem, we can c squared. Well, we got 20 squared is 400, and a we're gonna call that well, I can call it x, and b I can call y. It doesn't really matter, but let's call that. So I'm going to let a equal x squared and b equals y. So now I'm going to use what they call implicit differentiation, because remember we have this, yet we have the x and y, but both of those in their background they have a t, so it's a function of time. So if I take the derivative of 400, right, that's 400 with respect to time, well, that's a constant, so that goes to 0. See it? Now over here I'm going to take, remember that I'm going to take care of this thing here. So what I'm going to do is take x squared. Well, x squared, the derivative of x squared, isn't it, is take 2 and subtract 1. But now, since in the background we know that x is a function of t, I'm going to have to multiply by dx dt, you see, right there. And now we're going to take 2y, the derivative of y squared is 2y, times dy dt, because we know that implicitly there's another variable in the background. That's why we call it implicit. So here we have 0 is equal to 2 dx dt plus 2y dy dt, right? So I'm going to solve for dy dt, you see. So by doing that, I'm just bring this guy, I'm going to try to solve for this dy dt right here, see it? So by the time I do it, I'm going to have that it's going to be equal to minus x over y, minus 2x over y. So here I'm just doing the algebras. If you can take a look at it here, I just brought that over to this side. I took this guy, this term, and just moved it over to here. See it? Then I divided both sides by y. I guess this is not correct here. Let me get rid of this. I went ahead and did it over here, so don't worry about this guy right here right now. I am trying to find dy dt. That's the what we're supposed to find. We know what dx dt, see, it's right there. But now what about dy dt? Well, I'm just showing the algebra. So now I'm trying to get dy dt, right? And I can see that it's going to be equal to dy dt is equal to this. However, we know what dx dt is given to because it's up here, see it? And that's equal to 2 feet per second. So then I have dx, so now I can put in for x. You see I can get to 2 right there. Okay, so let's see what we got here. So dy dt is going to be equal to, remember I'm trying to solve for dy dt. Okay, so now that's going to be equal to minus x over y dx dt. However, we know that dx dt is going to be 2, right? See it right here, 2 feet per second. So I'm going to replace this thing with 2 feet per second. See it right here? It's coming from here. So now when I do that, I'm going to have minus x over y times 2 over seconds. So basically I have solved now for dy dt is going to be equal to minus 2 x over 12, which can simplify to minus x over 6. So we know that dy dt is going to be equal to dy dt is going to be minus x over 6. However, now we look for x. So in order to solve for x, we go back to this Pythagorean theorem, because remember, we know that the y value is going to go out to 12, correct? I mean 12 units. When this thing measures 12 here, whatever that does measure. So at that point, I do know what I know what y is. It's 12 feet, right? So if I take a look at this, let's go back to here. So I move this up a little bit. Okay. So what I have is that this thing here, you see, let me put it right here. Right here, see, dy. So I need to solve for x. Well, remember we had the Pythagorean theorem, right? So if I'm trying to find out what x squared is, right? So what we had is 400 minus 144. Well, why is that? Because remember over here 400 was equal to, and then I had x squared, right, plus, and then we had y, and y squared. Okay, so now we have 256, right, and 16. So we're trying to solve for y. So I mean, sorry, for x, right here, and over here we have y squared, if you call. So we know that y is 12, right? When y is at 12 feet. So I can put that in here. So I have 400, right, equals x squared plus, and then 12 squared. Y is equal to 12 squared. You see that? This is feet. That's 144. So then I have x squared equals, I'm going to take away what that equals. That's going to be equal to 256. So then I'll take the square root of both sides, right? So then I have x is equal to, and if I take that, x is equal to, so then I have what? 215, that's 16. That's 16 times 16, right? It's 256. So now I know what my x distance, now I know what the x, how far it's gone away from the wall at that point. When it's come down, y has come down to 12, x has gone out to 16. So now our final thing to find out was, we had dy dt, you see it, equals, now remember over here it was minus x over 6, if you recall that. So we had minus x, which we happen to know is, see right here, x over 6. So now we happen to know what x is, right? It's equal to 16. And then we have 16, right? And then over here we have in 6. So, and then that's times feet per second. So what we have here is that I can simplify that, and I can have minus, what, 8/3. It doesn't look very good. 8/3. See it? 8/3, and then it's going to be feet per second, and that's going to be the answer. Let me put that in black. So that's going to be equal to minus 8/3 feet. That's the rate at which it's the dy dt is coming down. It's going 8 mine going down minus 8/3, 2 feet something. Right, so per feet per second. And that's the answer. So that's how we use one example of what we call related rates. I'll do another example here shortly, but that's good.